Hey there, welcome to video 16. Today we're going to talk about beta independence. A transistor is beta independent if the Q point of the transistor remains relatively unaffected by changes in beta. You know, beta can change with temperature, VCE, and especially from one transistor to another. Most of the time we want our circuit to have a very stable, predictable Q point, and that can be kind of hard to do sometimes. All right, let's take a look at this circuit I've got up here. We've seen this before, or something similar to it. I've crunched through all the numbers and put the load line up here, and here's what we've got for this circuit. We've got IC sat of 6 milliamps, VCE cutoff is 15 volts, and our Q point is exactly centered on the DC load line, 3 milliamps ICQ, 7.5 volts for VCEQ. Now, this is all predicated on the assumption that our beta is 100. All right, what happens if we happen to grab a transistor that had a high or low beta compared to 100? Well, we're going to take a look at that. I've already done the load line Q point locations, and let me drag that load line over here, and let's take a look at what we've got. All right, if we happen to grab a transistor that had a beta of 50, that moves our Q point over here from the center over towards cutoff, and we end up with 1.7 milliamps ICQ, 10.8 volts for VCEQ. That's kind of far away from what we wanted, so that's probably not a good situation. And similarly, if we had a transistor with a beta of 200 in this circuit, the Q point moves towards saturation. We end up with ICQ of 5 milliamps, VCEQ of 2.5 volts. Again, probably not good. Finally, if I happen to grab a transistor with a beta of 300, our Q point works out to be in saturation. All right. Actually, if you plug the numbers into the ICQ equation for a beta of 300, it predicts collector current larger than 6 milliamps, but that's not physically possible, so our Q point stops right here at saturation. Remember, an NPN transistor has to be operating in the first quadrant. Okay, now what can we do to fix this problem? Because we don't want to be hand selecting transistors for some particular beta. That's just not practical. Well, here's what we're going to do. Let's take a look at this equation for ICQ. These IC sat and VCE cutoff, they're totally independent of beta anyway, so it doesn't affect them. But this one does. So let's take it down here on the next page, and in order to obtain beta independence, what we want is to make the RB over beta term small compared to R sub E over the expected range of beta. Now we can write this as an equation. R sub B over beta should be very, very small compared to RE, or equivalently, beta times RE should be very large compared to R sub B. And this much greater than symbol means typically at least a factor of 10. All right, this can be hard to do for a lot of design applications. We often have conflicting requirements. For example, we can't just go setting RB to 0 or make R sub E arbitrarily large, because that can screw up other things that we're trying to shoot for. So what we can do is try and come up with biasing arrangements that allow us to more easily meet either one of these inequalities. They're equivalent. And that's going to be the subject of our next video. We're going to talk about a biasing arrangement that makes it very easy to obtain beta independence with a single power supply. And that's the subject of the next video, and I'll see you then.